Welcome to you all in my YouTube channel Express Mathematics. In today's video, I am going to explain you about decomposition of a vector in the plane. Before starting, I want you to make sure that you please subscribe my channel right now so that I will be encouraged to make more videos, and also press bell icon so that you will be informed about my coming videos. So now without delay, I am going to start today's topic, decomposition of a vector in a plane. So every vector in a plane can be expressed as the two given vectors in the plane, okay, in terms of two given vectors in the plane. If vector A and vector B be two non-zero and non-collinear, be two given non-zero and non-collinear vectors, then every vector are in the plane can uniquely be represented as the sum of the two vectors parallel to vector A and vector B. Okay, so here A and B are two given non-zero and non-collinear vectors. Then every vector R in the plane can uniquely be represented as the sum of the two vectors parallel to A and B. Okay, so this R equals to some scalar times A plus scalar times vector B. In that way, we have unique representation, means we have only one type of representation. Okay, now let's prove it. For not to make the proof lengthy, I am explaining and not writing in much detail. Okay, O A O B. Let OA be vector A and OB be vector B, and let OP equals to vector RB in the plane of vector A and vector B. From P, let us draw P M parallel to BO and P N parallel to AO. Okay, so I am writing here insert here OA equals to vector A, OB equals to vector B, OP equals to vector R, and let us draw PM parallel to BO and PN parallel to AO. Now using parallelogram law of vector addition, we can write OP vector equals to OM vector plus ON vector. Here OM and ON are the adjacent sides of the parallelogram OMPN, because this PM is parallel to BO and then PN is parallel to AO. So this OMPN is the parallelogram, so we can use parallelogram law of vectors, and OP vector equals to OM plus ON. And as OM and OA are collinear, so OM equals to, we can write scalar times OA. So here equals to, we can write OM equals to X times OA vector plus this ON and OB are collinear, so ON vector equals to, we can write scalar times OB vector, that means OY times OB vector. We can write this OP vector equals to this, and this OP vector equals to, we have already supposed that is vector R, therefore vector R equals to X times OA means it is vector A plus Y times OB means it is vector B. So here vector R in the plane we can represent as the sum of two vectors parallel to A and B. This XA vector is the vector parallel to vector A, and YB vector is vector parallel to vector B. In this way we have representation of vector R, and now we have to show that it has unique representation. Now we shall show that the relation is unique. Unique means it has only one representation, not more than one representation. For this, if possible, let vector R equals to X dash vector A plus Y dash vector B, where X dash and Y dash are, and Y dash are scalars different from X and Y respectively. Okay, so this X dash and Y dash are the scalars which are different from X and Y respectively. So combining these two, what we can get is X dash A vector plus Y dash B vector equals to X A vector plus Y B vector, and this implies X dash when it comes here becomes minus X dash minus X A vector, when this comes here becomes minus, and vector B will be common, plus Y dash minus Y vector B equals to 0. Okay, and since vector A and B are non-zero and non-collinear vectors, since vector A and vector B okay, here we shall show that the relation is unique. For this, if possible, let R equals to X dash A plus Y dash B, where X dash and Y dash are scalars different from X and Y respectively. And now combining these two, we will get X dash A plus Y dash B equals to X A plus Y B. And when X A comes here becomes minus, and vector A will be common, X dash minus A, X vector A. When it comes here becomes minus, so Y B will be common, vector B will be common, and Y dash minus Y vector B equals to 0. And since vector A and vector B are non-zero and non-collinear, X dash minus X equals to 0, Y dash minus Y equals to 0. This implies X dash equals to X, Y dash equals to Y. Okay. Hence the relation is hence the relation is unique. So this completes the proof. In this way, we have represented vector r in terms of two vector a and b, given vector a and b. This shows that every vector in the plane can be expressed as the vectors parallel to two given vectors. And we also have shown that this relation is unique because we have supposed scalar different from x and y, but the scalars became equal. That means the relation is also unique. Okay, in this way we can decompose a vector in the plane, or any vector in the plane can be expressed as the two given non-zero and non-collinear vectors in terms of two non-zero and non-collinear vectors. Okay, and this same relation can be used to prove coplanar also. So every vectors in the plane are coplanar, and if it is possible to show any vector, if it is possible to show any vector equals to any express any vector in terms of any other two vectors, then this vector, three vectors are coplanar. Vector r, vector a, and vector b are coplanar. So to show that any three vectors coplanar, also this relation is used. So we will express one vector in terms of other two vectors, or this is also called linear combination. If we can express any vector equals vectors as a linear combination of any other two vectors, then they are coplanar. Here vector r we have expressed as the linear combination of two vectors, vector a and vector b. So vector r, vector a, and vector b, they are coplanar. Okay, so this relation is also used to show any three vectors are coplanar. Okay. Thank you for watching. I hope this video is helpful, and if you have not already subscribed my channel, please subscribe it right now, so that I will be encouraged to make more videos, and also press bell icon so that you will be informed about my coming videos. Thank you very much.